So in this video, in this session, I am going to explain how to derive the energy of the electron. So in my previous video, as you see, I derived the radius of the orbits, and then I used this a force equation to do that. The force is the two forces that's holding the electron around the nucleus. One is the Coulombic force, and then the other one is the centripetal force. So I did use these two formulas to derive the energy of the electron. So these two, and if you're wondering where did I get this, I highly recommend you to watch my previous videos where I'm explaining how did I got where did I get these two equations here. So now let's go ahead and get started. To derive the energy of the electron, first, of course, we need the total energy, which is E is equal to kinetic energy plus potential energy. That's what we know from the physics. So here, instead of writing the normal potential energy, you know that the potential energy that comes from the Coulombic attraction between the electron and nucleus. So we're gonna write this as E is equal to 1 over 2 MeV square plus, now for potential energy, we'll write the Coulombic attraction. 4 pi epsilon times R. All right, so now what we do, so here's the negative sign is important because it tells us the electron is bound to the nucleus. Now, next step is what we do is we're gonna associate this force equation into our total energy equation. So that's why I brought this force energy here. And again, I will highly recommend you to watch my previous video if you want to know more about this force equation. So why we're doing it, why we're going back to the force equation instead of just plugging the numbers here. So because right now the energy expression depends on the velocity here, which we don't want it. We don't want that velocity. So what we want is the energy purely in terms of radius or the quantum numbers. So we have here the quantum numbers, which is n. So we need to integrate. That's why we need to associate this the force equation into the total energy. So that's why we use something we already know here. Again, from the circular motion and Coulombic force, we know that this equation, the force equation, it's holding the electron tightly around the nucleus. I apologize, the nucleus. And so now our next step is what we do. We convert the force into the energy. So from there, from this equation, what we do first, we solve for R. And when we do this, so it's going to be equal to MeV square is equal to, we just multiply both sides by R, and if we do that, our R square, we should be get E square divided by 4 pi epsilon R. So here the right hand side is the proportional to kinetic energy here. So the left hand side, it looks like it's a potential energy without the sign. So now we divide this both by 2, and when we do this, we should be able to get 1 over 2 MeV square is equal to just gonna write that here. 1 over 2 is equal to E square 4 pi epsilon R. So what we have done is that we rewrite the kinetic energy in terms of now position instead of velocity. Because said, we don't need velocity here. So this is why we use the force equation, not just not randomly, but to eliminate this v, the velocity. So now what we do, we substitute back into the original energy with respect to this kinetic energy. So when we do that, we should be able to get E is equal to 1 over 2. We should be get E square divided by 4 pi epsilon r minus E square 4 pi epsilon r, and when we combine terms, we should be able to get E is equal to negative 1 over 2 times E square 4 pi epsilon r. So that's what we get. So now this result tells us the total energy is negative. So the electron is bound. The energy depends only on the radius. And as you see, the smaller the radius, the more tightly bound the electron is. So now what we do, we plug this into the second equation, which is the radius equation. So why we do this? So because now we bring in the result from the section 1, because this equation encodes the quantization condition. So right now the energy is continuous in terms of R, but in quantum mechanics it tells us that only certain radii are allowed energy. So by plugging in this equation, we convert energy into a function of n. So that's why we're using the we bring this equation back. So when we do this, we substitute this r. I apologize. So we substitute this r in with respect to that r. And again, why? Because this encodes the quantization condition. So when we do that, so I'm just gonna go ahead and write steps. So I'm gonna write it right here. When we do that, we should be able to get E is equal to negative ME e sub 4 divided by 8 epsilon square h square times 1 over n square. So I will let you to do that. So all you have to do is just to you replace it, and then you simplify it, and when you do that, you should be able to get this the final equation. So this is the energy of the electron. So what we have just shown then is the quantizing position. Automatically it quantizes the energy, and that's the bridge from the classical physics to the quantum physics.